Hi, Physics 1, Mr. Janowski. So here is the next part of the chapters 2 and 3 slides. So do now, let's go through this quickly. What was the average score on the mechanics baseline assessment? 19% was our average. And don't be upset about that because nationwide, physics students who are taking this for the first time, um, either in high school or in college, the average is right around 20% all the time. Very predictable because people have very strong misconceptions about physics. And misconceptions are going to be a big theme of what we're talking about today. So, in physics class, what is defined as a push or a pull? That is a force. All forces are pushes or pulls. So, true or false? Forces are required to keep an object in motion. That is false. You don't need a force to keep an object in motion. Forces don't keep things in motion. Forces change motion. So we'll get to that misconception on the next slide, or the next couple of slides. So we learned that there are two types of quantities. So question 4, quantities that only have a magnitude are known as scalars. So examples of scalars are age, temperature, things like that. Quantities that have a magnitude and direction are known as vectors. So force is a vector. Later, we'll learn that velocity is a vector, momentum is a vector, because these things have magnitude and direction. So question 6, what is this funny symbol and what does it mean in math and physics? That is a capital Greek letter sigma, and in math and physics, sigma means sum. Question 7, when is an object in mechanical equilibrium? It is in mechanical equilibrium if the sum of the forces on it equals 0. So its motion doesn't change. If sigma f equals 0, you have mechanical equilibrium. So we started chapter 3, Newton's first law of motion, the law of inertia. So here's Aristotle, who I'm calling Mr. Misconception, because he had a lot of misconceptions about physics, and a lot of people, even now in 2020, they still have the same misconceptions. So Aristotle believed that there were two types of motion. There was natural motion and violent motion. So according to Aristotle, and let me point this out explicitly, all of the ideas on this slide are wrong. These are Aristotle's misconceptions. These are what he believed, but they're wrong. So according to Aristotle, natural motion, it was natural for boulders to fall because boulders are heavy, and it's in the nature of heavy things, according to Aristotle, to want to be down. So if you pick up a boulder and you let it goes down because according to Aristotle, it's in its nature to be down. It's just a property of the boulder. It kind of wants to be down. Things that rise, things like smoke, well, it's in their nature to be up. So you light a fire, why does the smoke go up? Because according to Aristotle, it's in the nature of smoke to be up. So that is incorrect. Then we get to violent motion, which violent is a poor translation of what he meant here, but that's the one we always go with. So any motion that is imposed by an outside cause. So imposed motion would be a much better name, but we always call it violent motion when we're talking about Aristotle. So for example, according to Aristotle, a cart is heavy, and by its nature, it just wants to sit there. So if you want the cart to move, you need to impose a force on it, or your horse needs to impose a force on it. The horse needs to impose violent motion on the cart. This is what Aristotle believed. And a ship, it's in the nature of the ship to just sit there on the water. So if the ship's going to move, well, according to Aristotle, you must impose violent motion on it with wind or with oars or something like that. So those are his ideas about motion, and these ideas are wrong, but this is what he thought. And a couple of quick things about Aristotle's ideas about astronomy. So he got some things in astronomy right, but this is something he got wrong. So he believed that circular motion was natural for heavenly bodies. So you look up at the night sky and everything you can see up there, well, those are all heavenly bodies. They're different than the things on Earth, according to Aristotle, and they have their own natures. So he believed that the stars and planets and the moon move around the Earth because that's just in their nature. That's what they want to do. So first of all, the Earth's not the center of everything. So the planets don't go around the Earth at all. All the planets, including the Earth, go around the sun. Aristotle would have thought differently. He thought the planets and the sun go around the Earth. So he had that backwards. He would also have believed that the moon goes around the Earth. Well, that's actually true. The moon does go around the Earth. So, yeah, we agree with Aristotle on that. The moon goes around the Earth. We disagree with the reason why. According to Aristotle, the moon goes around the earth because that's in the nature of the moon. It's a heavenly body. It's got its own eternal properties, and one of them is it likes going in circles because circles are the perfect mystical shape. So obviously, the moon's going to do circles, according to Aristotle. And it doesn't need a force to make that happen because it's just in the nature of the moon to do circles. So, of course, now we know, well, no, you do need a force to keep the moon going around the earth. That force is gravity. We understand that now, but Aristotle saw it differently. And the reason Aristotle's wrong ideas are so important is because they really dominated this whole science for about 2,000 years. And for 2,000 years, everyone thought that if you want to keep an object moving, you have to apply violent force on it and impose motion on it, which we're going to find out is wrong. So skipping ahead 2,000 years, we get to Galileo Galilei. So he was concerned with how things moved, not why things move. So he wouldn't just sit around and think of, the rolling ball and ponder its nature and try to figure out why is its nature causing it to do it this way. He didn't think that way at all. He was more interested in, all right, well, let's watch it move and describe how it moves and see if that leads us anywhere. So he comes along and he disproves Aristotle's idea that forces are required to keep objects moving. And he believed that experiment and not logic is the best test of knowledge. You can't just sit in your chair. I know he's sitting in his chair in this portrait of him, but you can't just sit in your chair and logic your way through the universe. You're not going to figure out scientific truth that way. So then we watch this Feynman video, which I love, where he explains the whole nature of science. So I'll put a link to that video in the description to this video. And I won't go into too much detail here, other than the thing that's in bold. If it disagrees with experiment, it's wrong. And that is the whole key to science. When you're doing science, you have to check your ideas against the universe. You have to do experiments. You have to make observations. And if you're doing that, you're doing science. And if you're not doing that, you are not doing science. So that's really what decides. A philosopher would call that a demarcation criterion, but we don't need to know that. If you're checking your ideas against the universe, and if you're willing to accept the fact that sometimes the universe is going to tell you that your beautiful, wonderful idea is actually wrong, then that's what makes science science. So back to Galileo. So he tested his ideas about motion by rolling balls along ramps. So he noticed something. So notice in this first setup, we have ramp going down, flat part, ramp going up at the same angle that the first one was going down. And he noticed, you let the ball go, it speeds up, and then it cruises across the middle part, and then it slows down as it's going up the other ramp. And it does so in such a way that it gets up to the exact same height that it left at. Well, not the exact same height, because there is a little bit of friction, even in this case, that's going to take a little bit of the motion away. So it will get most of the way up. But if you can minimize the friction, you can tell that, it's trying to get back up to the same height. So that was interesting. And then he realized, well, I can actually change the angle of the second ramp. So now this one's not as steep. So ball speeds up, cruises across the middle, and then it goes up this ramp, and it slows down at a slower rate because this ramp's not as steep, and it travels further along this ramp. But the key thing is, well, it still gets up to the same height. So that was a very interesting result. But that's not the key to what we're going to talk about today. The key is what actually happens in the middle here. And what happens in the middle is the ball just goes straight line, constant velocity. And the reason it does that in the middle is because while it's in the middle, there's no net force on it. So on the first part, when it's going down the ramp, there's a net force. There's gravity overcoming the normal force, and the actual diagram for this is a little complicated. We'll get there later in the year. But there's a net force on the ball when it's on the ramp. It's speeding it up. At the end, there's a net force on the ball, and it's slowing it down. In the middle, no net force. There's still gravity pulling the ball down, but there's also a normal force pushing it up. Those forces exactly cancel, and so no net force. And while it's in the middle, it just goes straight line, constant speed. And he realized, well, you can make this middle stretch as long or as short as you want, and it's not going to change the end result of how high the ball goes. Because in the middle stretch, the ball just keeps doing what it was doing. And comparing this to Aristotle, in the middle stretch, the ball is moving without a violent outside imposed force causing its motion. So you don't need a force to keep things moving because forces don't do that. Forces change motion. So yeah, he disproved Aristotle's idea. And the reason Aristotle thought what he did, and the reason so many people still have this misconception, is because we live in a world full of friction. So if something's moving, if it's rolling along the ground, if it's sliding along the ground or along the ice or anything like that, there's going to be friction. So that's a force that's so always there in everyday life in things that we're used to dealing with, that you take it for granted and you overlook it. And so you start to think, well, it's trying to stop. If you push something across the ground and let it go, pretty soon it's going to stop. And you're so used to seeing friction all the time that you get this misconception in your head that to keep something moving, you've got to keep pushing on it. But if you could get rid of friction, or at least minimize it a lot, you'll start to see what's actually happening, which is if it's already moving and there's no force on it, it keeps moving. You don't need a force to keep it moving. If there's no net force on it, it just keeps moving. So then we get up to Newton. Here are Newton's birthdays and death days. Again, this is something to do with switching from the Julian calendar, created by Julius Caesar, to the Gregorian calendar, Pope Gregory the 13th. That's why he has two different birthdays and two different death days. Depends on where you lived at the time that Newton was born or died, what day you would say it was. So anyhow, Newton, probably the most important scientist of all time. Without Newton, we wouldn't have the scientific revolution. We wouldn't have the industrial revolution. And we wouldn't have the modern world. His ideas were that impactful. So he formulated 3 laws of motion, and today we're talking about the first one. So the first law, often called the law of inertia, restates Galileo's idea that a force is not needed to keep an object moving. So Galileo died in 1642. Newton was born the same year, according to some people, or the next year, according to others. Newton came along after Galileo, and he knew of Galileo's idea. And Newton's first law is just restating one of Galileo's ideas. So the first law says every object continues in a state of rest or of uniform speed in a straight line unless acted on by a non-zero net force. So if it's at rest and there's no total force in it, it will continue to stay at rest. If it's already moving and there's no total force in it, it will keep moving, uniform speed in a straight line, constant speed. So that is Newton's first law of motion. And so this image, very quickly, this is Newton's death mask. And I'll put a link to this video in the description as well. If you're interested in this, kind of neat historical artifact, the death mask of Isaac Newton, you watch the video. And then finally, we watched a couple of videos about the tablecloth trick. The first one is a very helpful how-to video on the tablecloth trick. The next one is the tablecloth trick being performed with lots of flair by a magician, talented magician. He's a magician. That's the tablecloth trick. And then if you were in class, we actually did the poor man's version of the tablecloth trick, using your palm as the table, a playing card as the tablecloth, and a penny as the plates on the tablecloth. And then, here's the slide. Well, I'll just leave this up for a second. This is the slide that explains when we made the switch from the Julian calendar, named after, the Julian calendar was basically the creation of Julius Caesar, probably somebody who was working for him, not him himself. But it's called the Julian calendar. Julius Caesar put it into effect. And that worked for a while, but then ultimately we all switched to the Gregorian calendar, named after Pope Gregory the 13th. So you'll notice there are days missing from this calendar. That was part of what Pope Gregory did. He said, October 5th, 1582, that day never happened. He just took it off the calendar. Interesting if you like weird historical, tangents. So anyhow, Newton's first law. Hopefully that helped.